We are going to discuss the second half of this chapter, starting with the cell potentials. Before we discuss this, first thing we need to understand here is what has caused electron to move from one place to another. And of course, if you imagine electron as a box, in order to have this box to move from one place to another, there gotta be a force. So let's focus on this so-called force for a minute. I hope you guys still remember there's one statement that pretty much every general chemistry teacher keeps saying. Metal intend to lose electrons, while non-metal intend to gain electrons. This gaining or losing electrons actually can be put up in one scale, just how easy or how difficult to lose electrons. And we suddenly realize elements have a different ability to lose electrons. In other words, one element will be more easier to give up electrons than the other. Like metal is easier to give up electrons than the non-metal elements. Throughout the years, people have done a lot of study on the various metals in, of course, searching for electrodes for their batteries. Remember, metal in general are electroconductors and good electroconductors. So this is what they have found, the order of its so-called electromotive force of the metals. So they find out that elements in group 1A in general has more electromotive force than elements in group 2A. Aluminum comes to the third place, followed by the first row of transition metals, exclude, of course, the copper. Then it is followed by the hydrogen. And you may wonder why we put hydrogen here, because hydrogen is a non-metal gas. And well, we will discuss why we put hydrogen here later on in our discussion. The last place will be the elements in group 1B that includes copper, silver, and gold, and then mercury. This series actually reminds us something. Let's talk about electronegativity. I hope you guys still remember the trends of electronegativity we discussed in Chem 1 class. As we cross the period from left to right, electronegativity increases. Okay, so when we look at this series, we suddenly realize it matches the statement we have just said about electronegativity. Group 1A, far left. Group 2A, second from far left. Transition metal sits in the middle, while group 1A, 1B, or group 1A, or group 1B, 2B, like a mercury, sits at the end of the D block elements. Does that have anything to do with electronegativity? Sure. Because the less electronegativity, the poorer of their ability to hold up electrons. In other words, the less electronegativity, the easier for atom to lose electrons. Suddenly, this EMF can be closely related or can be explained by the electronegativity that we have learned. All right, so from this EMF series, we suddenly realize that a metal with the more EMF, and of course, must have the less electronegativity, is easier to give up electrons. As a matter of fact, EMF applies to all elements, including non-metal elements. But we understand the metal intend to give up electrons, while metal intend nonmetal intend to gain electrons. So here, nonmetal is something that we probably refer as graphite, because graphite is an excellent electron conductor. Now, let's imagine if we have two pieces of metals next to each other in a cell. Before we close the switch, these two do not have electron flow from one place to another, but however, there is a potential building up inside of these two pieces of metals. How do we know that? First, two pieces of metal, as long as they are different from each other, they have a different EM force within. Okay? So electromotive force within. The one with a greater EMF will have the push much greater to the electrons. But of course, there's a block. The block is being the switch. But the electron will feel more push than the electrons in the other piece of metal with a less EMF. The greater the push, the greater the pressure. The greater pressure, and it can be considered as the greater the potential. So the potential here is a measurement of a material to give up and push electrons to the cathode. Once we have the switch closed, the metal with the greater EMF will push electrons to the other side. And of course, the electrons are going to keep on flowing until the potential or potential energy on both sides are equalized. They have the same level. They have the same amount of pushing force. So after we have explained this potential, so we realize potential is essential for us to have in the battery, because potential actually can push these electrons around from anode to cathode and form a circuit so that the electron can go from the anode all the way to the cathode. Since the electron is moving around doing the work, and from chapter 5 in Chem 1 class, we understand work is a form of energy transfer. Just which form of energy has been transferred to what form of energy? Apparently, the potential energy caused by this push is being converted to the kinetic energy of the electrons. Since the electron is doing work by moving around, and according to physics, the work done by electrons is equal to negative I times T times the potential of the cell. And potential of cell is equal to E, the potential of a cathode that undergoes reduction reaction, plus the potential of anode that undergoes oxidation reaction. What we first think about here, or to understand, is the potential of a cathode is just how easy it is to conduct the reduction half reaction, while the potential of an anode can be considered as how easy it is for that piece of metal to conduct the oxidation half reaction. So that is why when these two combine together with the circuit, we suddenly realize it is a win-win situation. So that's why we have adding sign, the add sign between the two. In that equation, I is electron current, T is the time of a current passing the circuit. When we multiply these two together, actually it winds up with the total charge of passing through the circuit. Total charge in chemistry can be considered as the total number of electrons passing. Because if we divide total charge by the charge of each individual electron, we know just how many electrons has passing through the circuit. In order to relate this circuit thing or physics with the chemistry, we must say, okay, so in a voltaic cell or the galvanic cell, delta G, the Gibbs free energy of the spontaneous redox reaction, is the theoretically converted to the kinetic energy of electrons only. That means it only does work. No Q, no heat whatsoever. In this way, delta G equals to W because Q equals to 0. And then W, according to the equation given, is equal to negative I times T times E cell. And of course, we can replace I times T with the total number of electron passing. That would be the mole of electron times a constant times the potential of the cell. And this equation right here is one of the powerful equations. And later on we'll see this equation is equivalent to the delta G equals the delta G0 plus RT log of Q in the chapter of 18. And here is the moles of electrons has been transferred in the redox reaction because we focus on electrons moving, right? So N is the moles of electrons. How do we know the moles of electrons? Remember, the third task when we balance chemical equation is to figure out just how many electrons must be equal amount, right, in losing and gaining electrons. So we need to figure out the number of losing electrons equal to the number of electron that gains. In turn, that means losing and gaining electrons must be equal in terms of moles. So this is how we figure out the moles of electrons. F actually is called a Faraday constant. It is the charge that one mole of electron carries. If you have a calculator, you can actually calculate the value of Faraday constant by using that equation I provided to you. 1.0602 times 10 to the negative 19th coulomb is the charge of one electron carries multiplied by the Avogadro number because that is the number for one mole of anything. Multiply them all together, you should be able to get 96,485 coulombs per mole of electrons. Delta G equals to negative N times F times E cell is, like I said, one of the most powerful equations in this chapter. Because not only it tells us how we can figure out the delta G from the potential of the battery or the cell, delta G also tells us the spontaneity of the process. In other words, E cell, the potential of cell, actually can tell us the spontaneity of the reaction. Remember, between delta G and potential cell, there's a negative sign. Negative sign means if delta G is less than 0, meaning this process is spontaneous, the potential is greater than 0. By the way, this potential is a state function as well. The reason for that is delta G is a state function. F is a constant regardless of the state. N is fixed if two states has been set. Think of this way. If we know the products, if we know the reactants, how many electrons have been transferred within this reaction is pretty much known. So N is also fixed. So delta G divided by the constant winds up a state function. So we realize that the potential of the cell has the opposite sign from delta G in order for us to predict the spontaneous process. If the potential of cell is less than 0, that means we are talking about a non-spontaneous process. In this case, remember, if we have a cell that's negative, negative or negative, make delta G positive. If potential of cell is equal to 0, we understand that the redox reaction reaches the equilibrium as delta G equals to 0. In reality, when we have a battery, these two actually would not occur. Because when the battery is completely dead, which is very unlikely in our real life, this is the case where E cell equals to 0. If E cell is less than 0, it's not going to happen in our battery. It will happen, however, if we have a rechargeable battery, which the electrolysis going on can have this E cell negative than 0, but less than 0, which we'll talk about later on at the end of this discussion. Just like a delta G, and potential can be under the standard condition or standard states. So that means we follow the definition of standard states, like 1 mole of solution, 1 atm for all gas. All the things must be stable at 298 degrees Kelvin. And there's one more condition that we have to follow in order to get a standard cell potential. No electric current. Why there's no electron current? That is because once we have electron current, the circuit is going to get hot because of the resistance. Every piece of metal, no matter how good conducting it is, it's always have a resistance at room temperature. So in order to follow our condition with the Q equal to 0, the cell does not generate heat, I must be equal to 0. So from this discussion, I equal to 0 makes sense. And we can have a delta G0 equals to negative N times F times E0 of cell. And that is what we call the Faraday equation. So once we have the standard reduction potential of the cell, we need to take a close look at it. According to our discussion of a potential cell, so we realize that the standard potential of cell actually is equal to the standard potential of cathode undergoing reduction plus the standard potential of anode, which is undergoing oxidation. Nothing wrong with it. Remember, as we already discussed, those potentials showing just how easy it is for those electrodes to conduct the reactions they're supposed to undergo. But I'd like to recall about reduction and oxidation being mutually reversed each other. This is something that we have discussed in the first half of chapter 19. If we talk about the same species undergoing reduction or oxidation, if you want to reverse it, so say, if you want to reverse the oxidation to the reduction, we have to change the signs, right? We have to change the signs of delta G. If we change the sign of delta G, that means we change the sign of the potential. In other words, we do not have to worry about potential of oxidation anymore. We can simply replace those with the potential of reduction with a negative sign in front. In this way, we unified the potential of reduction, potential of oxidation under one scale we call the potential of reduction. And the negative sign certainly makes sense when we try to think about it of a delta. Cathode is the final state for electron to go in, and anode is the initial state for electrons to come out. So this equation, E0 cell equals to E0 of cathode minus E0 of anode, becomes quite important because all we have to do is to check the value of a reduction potential of everything. And once we know which one's cathode, which one's anode, we just simply subtract their standard reduction potential in order to have the standard cell of that potential, the potential of cell. When we do the subtraction, there must be a reference to tell us at which point there's going to be certain value. So here we choose hydrogen. So that is the reason why hydrogen is listed in that EMF series, to compare just how many metals that is more active than hydrogen and how many metals that are less reactive than hydrogen. We use hydrogen here as a standard potential, so we call it standard hydrogen reduction potential. And from the setup, we realize that we need 1 atm of hydrogen gas bubbling through the solution, and the solution must be kept as 1 molar of hydronium in it. Whatever the potential we measure here is being set as a 0.00 volt. Such potential or such electrode is what we call the standard hydrogen electrode, short for SHE, so She. And here I give you just how we're going to write the standard hydrogen electrode as either cathode or the anode. And I want you guys to understand. So first we need to realize where this salt bridge is, and we're going to write for the anode with oxidized species 2 or reduced species to oxidized species. This is where we indicate the electron flow. And for the cathode, oxidized species to reduced species, this is where the electron flows. So here is a table of a standard reduction potential for many substances, including the free element as well as ions and compounds, so on and so forth. And obviously we realize that for fluorine right here, it is a very positive. Everybody understand fluorine is the strongest oxidizing agent, because as we said in many occasions, fluorine gas will do anything to grab an electron to itself in order to make itself octet. Grabbing electrons, oxidizing agent, right? Itself undergoes reduction. And so that is why we're not surprised to see that we got a sodium, lithium sitting at the bottom of this table, because they intend to lose electrons. So from this list, we realize that the more positive the reduction potential is, the stronger the oxidizing agent it is. And of course, if you want to reverse it to say, the more negative this reduction potential is, the greater the reducing agent it becomes. Remember, reducing agent undergoes oxidation. Oxidation is a reverse of reduction. So that is why if you have a negative sign in front of reduction potential, that actually indicates oxidation reaction is favored. Oxidation half reaction is spontaneous if you have a negative sign for reduction potential. So this is some reminding I want you guys to realize. So like I said, the more positive E0, the stronger the oxidizing agent it becomes. And then we'll come back to this slide to get the values from time to time in our discussion. All right, now let's get used to this standard potential a little bit more by conducting this example problem. So here we're going to use the table of standard reduction potential in the previous slide to answer all these three questions. First question. The question wants us to know whether this setup works or not as a cell. If it does not work, if it doesn't work, so what are we going to do about it? If it works, so we are asked to calculate the standard cell potential, and later on we're going to calculate the standard free energy change of this spontaneous reaction. When we look at question A, so let's analyze this shorthand notation of the cell. We realize the first half is everything going on in the anode chamber. You're right. This is for the cathode chamber. Therefore, the reaction occurs on the anode is iron form iron 2+. What we're going to do here is we're going to write them up using the reduction potential. In order to have the reduction potential, the reaction must have electrons as the reactant for both electrodes. For the anode, Iron 2 plus gains 2 electrons to reduce to the iron metal. For the cathode, aluminum gains 3 electrons to form aluminum. You start to think a little bit awkward because we understand for an anode, there's oxidation going on. Why suddenly we write them into the reduction? Because we are going to use the value of reduction potentials for each reaction. As we copy down the value, we find out that iron has a negative 0.45 volt. Negative means reduction is not favored. The oxidation actually is favored. And for cathode, and we understand cathode is where the reduction happens. So this is potential we have. Meaning what? Meaning the reduction is even less favored. All right, so with both half reaction written as reductions, we understand the standard potential of the cells equal to the standard potential cell of cathode minus that of anode. We wound up with a negative 1.21 volt. Negative volt times negative N times F, negative or negative winds up a positive. We understand we have a non-spontaneous process. This design of a cell does not work. So how are we going to make it work? We understand if we have a process that is not spontaneous, the reverse one must be the spontaneous. In other words, all you have to do is to reverse the reaction. How are we going to reverse the reaction for the cell? We switch the electrode chambers. What used to be cathode now becomes an anode. What used to be anode becomes to the cathode. So the new notation, of the cell is we have aluminum in the anode chamber, iron in the cathode chamber. And in this way, we change the sign of E0 cell. Since E0 cell is a positive, we understand it is a spontaneous process. As for the question C, it is asked for the delta G0. So delta G0 equals a negative N times F times E0 cell. We know the E0 cell already. F is a constant, no problem. Our challenge here is, what about N? Meaning total number moles of electrons that pass through this reaction. How can we find the number? Here. 2 and 3. The least common multiple of these two numbers, you got it, 6. That means we multiply the first by 2. We multiply the third by 3 in order to have the overall balanced redox reaction. So we realize there's 6 moles of electrons. So N equal to 6. Plug the N equal to 6 into the equation. We figure it out, it's a negative 700 kilojoules per mole. So here I just give you how we make up 6 moles of electrons as a total number of mole of electrons in this reaction. There are some important features about standard reduction potentials, either for the individual reduction potential or the self-potential. The value of a standard reduction potential of the species actually tells us just how strong or how weak this species or this couple as oxidizing agent or the reducing agent. The more positive it is, the stronger oxidizing agent it becomes. Vice versa, the more negative the standard potential, reduction potential is, the stronger the reducing agent. But also we can use a standard reduction potential to explain, to predict, finally, the product of a single displacement reaction, along with any other redox reactions. So here's what we're going to do. This rule is called the northwest-southeast diagonal rule. Our first step is to arrange the table of standard reduction potential from the most positive at the top to the most negative at the bottom. So for example, we got the zinc and copper. By checking out the value, we found out the copper is positive while zinc is negative. So that's the reason why we put the copper on the top, because it's more positive than that of zinc. Here comes the half reaction of reduction of copper. So reduction half reaction of the zinc, because once we decided where we put the standard reduction potential, here comes the half reaction. As we now realize, we put the copper on the top, zinc at the bottom. We're going to draw a diagonal from northwest to southeast. That means the substances on the left of this half cell equation will, copper 2, will oxidize the substance appearing on the right of the half cell reaction located below it. Copper 2 plus on the left of the first half reaction will oxidize the zinc that's on the right in the half reaction. I just want you guys to understand that both half reaction must be in reduction. And that is how we're going to set up as the potential as a cell. So we put the copper and the copper 2 plus in the cathode chamber. We put the zinc and the zinc 2 plus in anode chamber. And once we have the cell, we understand that the standard potential of the cell is equal to this 2 E0 subtracting. So we wind up as 1.10 volt. And finally, I just want you guys to understand this diagonal line indicates the two reactants of the reaction. We got the copper 2 plus, zinc 2 plus, indicated by, of course, this diagonal line. So this diagonal line tells us what are the two reactants gonna be for this reaction to take place. Of course, one must be the oxidizing agent, one must be the reducing agent. And from this picture, the one on the top must be oxidizing agent because it has a higher reduction potential. The one in the lower must be the reducing agent because it has a smaller value or even negative value of reduction potential, meaning the oxidation actually is probably preferred. One other feature about standard reduction potential is that it is an intensive property, while delta G here is an extensive property. What does that mean? And we're going to see that pretty soon. When we try to calculate the standard potential of the cell, we must realize the standard potential of the species is actually independent of the total number of electrons transferred in actual redox reaction. What does that mean? It means that if you have a cathode like this, I'm sorry, so there's a little bit of editing problem. And as for anode, we got aluminum. Why we put aluminum at the bottom? Because aluminum has a more negative value. According to that northwest-southeast rule, we must list the one with the more negative reduction potential at the bottom. And we understand for the cathode, it undergoes reduction. For the anode, it actually undergoes the oxidation. So that is the reason why these are the reactions that actually takes place. And what we need is multiply the first half reaction by 3, multiply by second half reaction by 2 in order to get that overall reaction. Remember, in order to get an overall reaction, we have to reverse one of the half reaction into the oxidation half reaction. This way, we can cancel out the number of electrons. And of course, the total number of electrons will be 6 moles. 2 times 3 or 3 times 2. And when we have done that, that would be the overall reaction. And the overall potential, as we can see, it is just -0.45 plus 1.66. Because remember, that will be the negative. So negative of negative 1.66. So that becomes the positive. And this arrow actually is what the rule tells us. We can put these two together to form the reactant. The only thing we need to worry about is what are the coefficients going to be. During this calculation, I want you guys to notice we didn't multiply those potentials by those multiples, which means the potential does not change when stoichiometric coefficients are changed in a balanced chemical equation. For example, if we multiply the entire equation by 2, the potential still is going to be the same. That certainly explains if we have a various size battery, as long as there's the same type, same reaction going on, they always have the same voltage. For example, we have a AAA, AA battery. They both has 1.5 volts. That is not going to change, regardless the size of the battery. Meaning, the voltage, the potential of the battery is intensive property. It does not rely on the size or the volume of the reaction. On the other hand, delta G is extensive property because the more the reactants we have inside the battery, the longer time span the battery lasts. That's what delta G is. So I just hope you understand, do not get confused. Why can't we just multiply those potentials as we multiply those reactions? Because potential is an intensive property. It has nothing to do with the multiplication of the half reactions. Another feature I'd like to talk about here is how this standard potential can be related with the delta G0 and KEQ. These two are the ones we discussed in the last chapters 18. From chapter 18, from this chapter, according to Faraday equation, delta G0 equals to negative N times F times E0 cell. And if you recall, the same delta G0 is equal to negative RT times log of K. K is equilibrium constant. And with that equation, we can definitely solve for E0 if we know the equilibrium constant is for this reaction. And of course, vice versa. This definitely establishes the triangle relationship between the three, which we're going to talk about in a few minutes. But I would like to point out here is at the standard condition or state, R, universal gas constant, is a constant. F is called the Faraday constant. Temperature is 298 degrees Celsius, which is fixed because it's a standard state. We put all three together, so this is the value we get, 0.0257 over N times log of K. Most of the time, we prefer to use a common log instead. Therefore, that the 0.0257 becomes 0.0592. And if you're interested, you can find out just how math is behind this calculation. Like I said, E0 of cell, delta G0 and K forms a triangle relationship. And from those equations, so we now perfectly clear about just what kind of value we're looking for in order to predict the spontaneity of the process. Delta G is equal less than 0, which means potential cell must be positive, K must be 1 or higher. Non-spontaneous, delta G must be positive, K must be less than 1, and potential must be less than 0. And at equilibrium, both delta G0 and E0 cell be 0. K, according to the log of 0 equals to log of K, K must be equal to 1 because log of 1 equals to 0. And remember this equation. This equation, as I called the most powerful equation in chapter 18, and we're still going to use this equation by plug in the delta E cell for the delta G, E0 cell for delta G0. In this way, so we have delta G equals a negative NF E of cell equals to delta G0 now being replaced as negative NF E0 of cell plus RT times Q. Remember, Q is a reaction quotient. It has the same formula as K, but the concentration we use here are the initial concentrations. At any temperature, so this is the equation we have. E cell equals to E0 cell minus RT over NF times log of Q. And that is what we call the Nernst equation. Just like the delta G equal to delta G0 plus RT log of Q, the most powerful equation of chapter 18, Nernst equation is the most powerful equation in chapter 19. Because that equation links pretty much everything that we want to discuss all together. At the 298 Kelvin, while the other thing could be different, RTF, they all becomes the constant, so we use a 0.0592 to replace all three. And And this is the one particular equation that I want you guys to realize. And for this equation to take place, it must be 298 Kelvin, because this is the only condition that we can have temperature plugged in for this value of 0.0592. All right, so one of the applications for cell potential is to determine the pH. So probably in our experiments, okay, you probably experienced virtual experiments, I like to say. You experienced that we can actually measure the temperature or measure the pH by the so-called pH meter. So how is the pH meter going to work? What is the math that support such pH meter? So here, this is the diagram for how we measure the pH using pH meter. Actually, now these two are very much combined within each other into one, so that there's two lines coming out, two wires coming out to connect whatever the instrument that can actually tells us the pH is. This is an example of the cell setup for us to measure the pH. This, as you understand, this is a hydrogen electrode that is on anode, and this is a reference electrode. We call it reference cathode because this is on the cathode side. According to this setup, our goal here is to try to figure out what equation we can use to replace that question mark, which is the concentration of hydronium or proton. And of course, we can get a pH. So once I have a pH, then we know what the concentration of proton is. Since this is a cell, so we understand the potential of this cell equals to the cell of the reference at the standard state. Why standard state? Because it has 1 molar of its concentration. And if you can control temperature at 298 Kelvin, which is quite as a room temperature, so we can use a standard potential of this reference electrode minus the potential of this hydrogen electrode, which is an anode. Remember, the half reaction that occurred in the anode chamber is this. We have hydrogen as what? The product, and we got H plus as the reactant. So that means if we use the Nernst equation for potential of hydrogen electrode, this is a standard state minus 2 electron as the moles of electron right here. So 0.0592 divided by 2 times the log of partial pressure of hydrogen divided by the square of concentration of hydrogen. If we consider the partial pressure of a hydrogen as 1 atm, as we put it in here, right? We put it in here, so we make the hydrogen as 1 atm. So make the hydrogen inside the tube is 1 atm. And we only have one variable right here, which is the concentration of hydronium. And I also want to report log also is available. So that potential of this hydrogen electrode is equal to negative 0.0592 times pH. And plug it in, We got a negative and a minus sign in between. So E0, E cell equal to E0 of reference plus this of pH. Then we can figure out the pH by using this equation. So all we have to do is we input this equation as some kind of a computer language into that instrument. So once it measures the difference of these potentials, and they can automatically convert that into the pH and showing up. So we know what the pH of the solution it is. All right, as we move on to the last example of this chapter, I'd like to remind you this example problem is comprehensive. It basically covers everything that we have discussed so far about a galvanic cell. So we have this set up. There are a lot of questions asked, total 6 questions, and we're going to answer these one by one. So first question, what is the half reaction occurring on the cathode? With the electron flow going like this is the electron flow going like this, we realized copper is where the electron coming out, that is the anode. Electron going in is what we call the cathode. So we focus on the reaction that occurs in this beaker. So in the cathode, we understand that that's platinum. Platinum does not involve in the reaction because I do not see PT with a certain positive charge in the solution. That means PT does not involve in the reaction. The function of PT is as a conductor to get the electrons into the solution. All right, so there are 4 species, as you can see: sulfate, proton, permanganate, and Mn2+. For the type of reaction that occurred in this cathode chamber must be the reduction, because reduction is not a vowel, right? So not starting with a vowel. So there must be a reaction going on the cathode. Since this is a reduction, half reaction, well, I need to remind you, electron must be the reactant. That becomes a golden rule for us to tell what we are going to do to make this half reaction work in this cathode chamber, even though we finish balancing the half reaction. That means it is okay for us to balance the half reaction without knowing which one is oxidizing agent, which one is reducing agent. Now, let's work on the half reaction. For the half reaction, we understand the species that has the common element is manganese. So we call these 2. Mn2+ to permanganate. What about the other 2? Sulfate. We know this sulfate show up in the other reaction, in other chamber, so that is a spectator ion. H+ actually tells us we're talking about acidic solution when we balance this half reaction. Like I said, it doesn't matter where we're going to add electrons later, because at the very last step, we'll correct this half reaction that it fits for the cathode chamber. All right, so now in acidic solution, we got these 2 species forming a half reaction. Balance the manganese first. As we find out, it is balanced. For the silica solution, we're going to add protons and water. We add protons, remember, when we balance chemical equation. We add H plus to the side with more negative or more oxygen. So 2 of the 3 statements apply here. This is why we are confident we're going to add H plus on the right with permanganate. Water is going to be on the other side with the manganese 2 plus. Balance this half reaction is quite easy because all we have to do is we add 8 H plus and we put 4 in front of H2O. Now we have every atom balanced in this half reaction. The next step is to balance this half reaction with charge. All right, when we look at what we have from the left, the total charge will be +2. When we look at the right-hand side, the product side, we realize the total charge is +7. Remember, we will add electrons on the side with the more positive. More positive by how much? How many electrons? That's going to be 5 electrons. We had just added the electrons on the product side, which means this reaction should be reversed, right? Because remember, for the cathode chamber, we're talking about the reduction where electron must be the reactant. So we have this reaction, half reaction, reversed to let it represent what is going on in the cathode chamber. Now let's look at the second question. What is the half reaction occurring on the anode? According to what we have discussed, according to the electron flow we have right here, we realize that the platinum is the cathode, that makes anode, then make a copper, then anode. And the half reaction that's going on, the copper must be the oxidation reaction where electrons becomes the product. And again, I want you guys to use this as a golden rule for us to make a judgment after we balance this half reaction. Remember, it is oxidation reaction, so we probably going to need to manipulate this equation, either reverse it or keep it in order to make sure electron is on the correct side. In this case, product. That means if we want to balance the redox reaction or the half reaction, we can do whatever we want. And finally, we just make sure we manipulate the reaction so the electrons stay on the right-hand side of this half reaction. So in a half reaction, we realize that the sulfate actually is spectator ion, so we can write the anode chamber. Okay, whatever that's occurred in the equation between copper 2 plus and copper. Remember, it doesn't matter where we put the copper 2 plus in this half reaction, because eventually we'll make adjustment. And since we have electron must be put somewhere in this equation, we realize electron must be on the left-hand side because we got the copper 2 plus on the left-hand side. In order to balance this equation, we need 2 electrons. And here, as we realize, we have electrons on the wrong side of the equation because according to our golden rule, electron must be product. So the half reaction on anode is copper yields copper 2 plus with 2 electrons. If you recall what we did in the previous slide, question A, the half reaction on the cathode is as such. Now, in order to make the overall cell reaction, we need to find some multiples to apply to the both half reactions so that number of electron gain equals to number of electron loss. As you probably already know it or remember it, what we're going to do is we're going to multiply the coefficient of electrons to another half reaction. So that is why for copper, we're going to multiply by 5. For permanganate, we're going to multiply this by 2. In this way, we got a total number of electrons, which is total number of moles of electrons later on in our calculation as a 10. Combine all these equations, both of the equations together after we cancel out the number of electrons. So this is what we have. All right, couple of things I would like to point out before we leave this slide. First, just for your information, total number of moles of electrons is 10. That means N in that Faraday equation is 10. And in question D, what is the E0 cell of the galvanic cell? And what is the K for this reaction? That is a simple question because we have just figured out the two half reactions. And we have labeled these two half reactions as a reaction on the cathode and anode. What we need is check those half reactions and find out what the standard reduction potential for each one is. And of course, I do have the habit to write the more positive one on top. So meaning this one is what's going to be on the cathode. And the one at the bottom is what we're going to be on the anode. Remember north, east, south, west rule. And it will tell us we have this, connect this in order to make the reaction to take place. But nevertheless, once we have this laid out and reduction potential on the cathode minus that of anode gives us 1.17 volt. That is a standard reduction, standard potential of the cell. I just want to remind you, N is equal to 10 moles from the previous slide. And according to the equation between the E0 cell and the K, we plug number in. So log of K equals to N times E0 cell divided by 0.0592. N equals to 10. E0 cell equal to 1.17. And we want up is 197.64. I'd like to remind you, we are dealing with an extremely large number. It does not may occur to you because it's a log of K. Remember, in order for us to get a K, we need 10 powered by the log of K. 10 raised by the power of 197.64. If you type this number in your calculator, you probably wind up the overflow error. But without a calculator, we can actually do something about it. Remember, 197.64 can be written as 197 plus 0.64. Remember, okay, if we have exponent in addition, that would be the two exponentials multiplied together. So we have 10 to the 0.64 times 10 to the 197. 10 to the 0.64 is a 4.4, so K is equal to 4.4 times 10 to the 197. We have already know 10 to the 23rd is huge. And if you recall, in a question of a diamond, and the year we figure out is some number times 10 to the 89. And here the number is even more bizarre, 10 to the 197. That means that this reaction is very, very much spontaneous. And again, before we leave this slide, I'd like to highlight what species in each chamber, ions, species in each chamber, because we're going to use that for the next two questions. This is as we know for the cathode. This is what we know for the anode. And for the anode, we realize there's only copper. And for the cathode chamber, remember sulfate shouldn't be included. So we got 1, 2, 3, 3 ions in the cathode chamber. So here I let them all out because we are going to use these for the next question. In this question, we want to know the change of the cell voltage, which is cell potential, on decreasing the ion concentration in anode compartment, which is anode chamber, by the factor of 100. First, we have our overall reaction. And remember in the previous slide, we noticed just what ions that are in each chamber. We understand the ion in the anode chamber is copper 2+. Why not copper? Because copper is a solid, right? Solid does not involve in the mathematical expression of Q, reaction quotient, as we already know. So all we have to do is to focus on these ions. All right. Apparently, there's some assumption that we have to go through. So say before the change, consider everything is under the standard state, which means the concentration for all the ions is 1 molar. And then let's see what happened after we decrease the concentration of ion in anode chamber. Remember, in anode chamber, it is only copper 2+ by the factor of 100. Now, the concentration has been decreased from 1 molar to 0.01 molar, which is 10 to the -2 molar, while the concentration of rest, which is in the cathode chamber, remains the same, 1 molar. All right, so with those initial concentrations all figured out, let's plug it in to these Nernst equation. We know what the E0 cell is, and this is the mathematical equation, mathematical expression of Q. Remember, so that's a square of initial concentration of manganese times concentration of copper raised by the power of 5 divided by so on and so forth, because these are the other two. Remember, coefficients becomes exponent in this mathematical equation. As we plug those numbers in, because we want the delta, the change of the cell voltage, so we subtract the E0 cell on both sides of the equation, so we have a delta E cell, and that's equal to this. Plug those numbers in, and we find out it's positive 0.0592 volts. Actually, by decreasing the concentration of copper 2+, the voltage increases a bit. What does that mean? From the Le Chatelier's principle that we learned from chapter 15, say if we decrease the concentration of a copper 2+, which is the product, equilibrium shifts to the forward direction. If equilibrium shifts to the forward direction, meaning the forward direction delta G is less than 0. If delta G less than 0, E cell has the value increases, right? Because delta G now has the value that's no longer 0, like equilibrium anymore. E cell must greater than E0 of cell, making delta E of the cell greater than 0. So now we realize the change of the voltage of the cell increases as equilibrium shifts in forward direction. That is another way for us to recognize the Le Chatelier's principle for galvanic cell. Now, let's talk about the changing concentration by the factor of 100 in the cathode chamber. And of course, we got the equation going on, and we just noticed what are the ions that are in the cathode chamber. And after change, we realize we have manganese 2 plus, permanganate, and hydrogen cation both have the concentration changed to the 0.01 molar, while the copper 2 plus stays at 1 molar. From the equation that we get from the previous slide, delta E cell is equal to this equation. As we put number in, we realize that these two terms cancel, and this is the value we get. It becomes negative 0.189 volts. The voltage decreases as we decrease the concentration in the reactants. You may wonder, yeah, manganese here is also in the product side, but as you can see, there's a 2 and 2, and then we start to see the net decrease in concentration of hydronium, which play the more important role here. All right, so from the Le Chatelier's principle, we realize as we have a concentration of hydronium decrease, equilibrium shifts to the left. If equilibrium shifts left, delta G for the forward reaction is going to be positive. If delta G is a positive, E cell must be negative. E cell is negative, it has the value that's less than E0 cell, delta E cell is less than 0. So from these two calculation problems, I just want you guys to realize how we understand Le Chatelier's principle in electrochemistry. All right. I just hope that I have explained this example problem 6 good enough, because this problem is a comprehensive problem that covers pretty much everything that we have discussed for the entire chapter 19 so far. Now let's look at some of the application of electrochemistry we have discussed so far, especially batteries. In this lecture, we're going to discuss 4 types of batteries. The first battery is called a lead storage battery, and you probably already recognize this is the battery we use in our vehicles, most of our vehicles. So far, we still have a hard time to get this battery replaced. The reason is this battery, first, is reliable. Second, it has the greater capacity as a battery. When we talk about capacity of a battery, I just want you guys to realize this actually is another way to let people understand delta G is bigger in this battery. Now let's look at this notation. So we realize, hey, we have a lead serves both as anode and cathode. This is a salt bridge here, and both sides has H plus, and as it turned out, the source of H plus is a sulfuric acid, and as a matter of fact, it's a strong, concentrated sulfuric acid. And these are the half reactions on the two electrodes, and the potential of the cell at the standard state is almost 2 volts. And we can actually put many of these all together to increase like 1, 2, 3, 4, 5. So we can put 5 cells all together in order to increase the voltage. So this is our first type of cell we're still using in our vehicle. And because lead is a toxic piece of material, the sulfuric acid is a strong acid, so that is the reason why the dispose of this battery is highly regulated. EPA even give money away to encourage the stores to help consumers to send this wasted battery to them, so that it doesn't cause too much of environmental damage. The second battery is the battery that we use a lot for the small devices. So this battery is called alkaline battery. And this type of battery gives the voltage, the potential of the cell, 1.50 volt. And as you can see, the bottom is the negative, so the anode. The top is cathode. Actually, cathode here is a rod of graphite. And these are the two reactions occurred on the cathode and the anode. And as you can see, why we call this battery as alkaline battery, because it has hydroxide in it. That is the reason why, if you want to use it, you better use it all of the capacity of this battery. Because if you want to if you have this stored in your device for a long time, it's going to leak out hydroxide. So that's why you can see something rusted over the time if you put this battery in the device for too long. The third type of battery is something that we see in our home improvement. Like in Israel, it has the battery. And the battery is called the nickel metal hydride battery. And they got a lot of pieces all together in order to increase the capacity of this battery. And the voltage it gives is 1.2 volts. And these are the two reactions that we can see. Why we call it nickel metal, we got the nickel, and hydride, this is what we call a hydride, that is absorbed on the metal. Sometimes it can also react to the metal. But nowadays, this type of battery is phasing out. It gives up to the fourth type of battery, which is the lithium-ion battery. The lithium-ion battery is the most popular type of battery that we use nowadays. It can be very small, so small it can fit in our laptop or in our cell phones. And the same type of battery can be very big, that is located in our hybrid car or electric car. Still, there's a lot of improvement going on to this battery. For example, liability. That means the battery still remains functioning after how many times of charging. Back in the year of 2000, let me think. Back in the year of 2004, when the first Prius in the United States, it wasn't very reliable because according to the news, the vehicle can be only charged like a few hundred times and the battery is out. In order to have people to buy such car or the vehicle back then, they put up a warranty for this battery of the car. Of course, you still have that kind of warranty, but the cost becomes much less as the technology improves over the years on the design of the battery. But nevertheless, as you can see, the cell reaction gives up 3.0 volts. And this is a reaction that occurred on both of the electrode. One other thing I'd like to talk to you about, it is not chemistry, is now that we are raising the trade war against China, unfortunately, China has the 70% of cobalt mine in this world. What does that mean? It means if we really have a war against China, we don't have a lot of choice about the lithium batteries anymore. Okay, we don't have much of a choice, and we don't have a lot of this type of battery in the country because they can cut off the cobalt, which is important material in this lithium-ion battery. All right, so I have just introduced the 4 common batteries that we see in our life. I also would like to talk about the fuel cell because fuel cell is our future, especially for our vehicles. If we want our vehicles still loaded with the fuel, so that we do not have to, pull over in the middle of nowhere because electricity is out in our car. The first generation of a fuel cell that is used for our mass transportation is called direct methanol fuel cell, DMFC. The cell gives up the voltage of 1.21 volts. It may not sound a lot, but imagine if we have 40, 50 the cells all together, so the voltage can be multiplied by 40 or 50, so that gives us enough of the voltage to power the car. These are the 2 reactions occurred on the anode. If you're interested, you can add up these 2 reactions together and you will see this is a combustion reaction of a methanol. So I just want you guys to realize for the heat of a reaction, delta G, delta S, as long as the same reaction, those values, delta G, delta H, delta S, are fixed. They are not depend on the path we choose for this reaction. We can either burn it or we can do something different, like we have the same reaction going on in the fuel cell. In this way, it doesn't generate a lot of waste gas, particularly nitrogen oxide, but it still produces greenhouse gas, carbon dioxide. That is the reason why this fuel cell is just for temporary purpose. Our goal is a hydrogen-oxygen proton exchange fuel cell. And as you can see, this is the cell that gives up 1.23 volts, almost the same. And if you combine this reaction together, you'll find out that's the reaction between hydrogen and oxygen to yield water. We do not burn hydrogen. We just let hydrogen pass through those tubes and let it react so that we can have electricity coming out. And someone claimed in China that once they put this thing, the fuel cell, into the car, the water, the car coming out, actually is good enough to drink. I don't know. I just report of what they did. And China is quite ambitious with this design, and the government has put a lot of money into this enterprise or the manufacturer to develop the fuel cell, put it in a car so that they can clean up the air, because right now the air condition quality is terrible in some places of China. All right, so these are the cells, our discussion about the cells. Our next slide, the last slide, I'd like to talk about electrolysis a little bit. I just want to touch the concept so that you know what is the relation between this electrolysis and the galvanic cell. Electrolysis is a process that we can use electric energy to drive a non-spontaneous reaction to take place. Actually, it is the reverse of what is going on in the battery or in a galvanic cell. So here I just wanted to put up these two pictures. Voltaic cell is a galvanic cell. It's another name of a galvanic cell because both guys, they studied pretty much the same thing at that time. So we named the cell after both of them. So voltaic cell is a galvanic cell. As you can see that the cell generates 0.48 as its voltage, and oxidation occurs on the anode. So zinc gives up electrons going to the copper, so that the copper consumes the electron by having copper decomposes. So that is the overall reaction. Once we use up pretty much like 70 or 80% of zinc, this reaction kind of stops. Why stop? Because according to Nernst equation, if we have too much of the concentration in this anode chamber, okay, so reaction stops. Remember, what we want is decrease the concentration of the anode chamber so that we can have this reaction moving forward. As we're going on and on, if the concentration of zinc 2 plus is too much, according to Nernst equation, the potential becomes to 0. That means the battery is out. Fortunately, this battery can be recharged. It's rechargeable, can be charged. So what we're going to do here is we're going to put the negative sign, so we put a negative charge, okay, on the tin and positive on the copper. So we push electrons going backwards. If we push electron going backwards, we reverse the reaction. Since this reversible reaction is non-spontaneous, that requires the input of electric energy at all times, continuously and external. So as you can see, the overall reaction is the reverse of what's going on in the voltaic cell. Now some terminologies. In this electrolytic cell, we still have anode cathode, but what used to be the cathode in the voltaic cell now is anode. Why this anode? Because we force this electron coming out of the copper. So still the electron coming out is what we call anode. For cathode, that was used to be the anode in the voltaic cell because we force electron to go in the tin. So that is why anode has the positive charge while cathode has negative charge, what we call the electrolytic cell. Still, the statement of the reactions started with the vial occurred on an electrode starting with the vial. That statement still applies for the anode and oxidation, and the cathode undergoes the reduction. But as for cell reaction, there must be the reverse reaction of the one in the voltaic cell. Of course, in the voltaic cell, reaction is spontaneous, and for the electrolytic cell, the reaction must be non-spontaneous. And that is it for the second half of chapter 19. And the key concept of this half of chapter 19 is potential. We have potential of reduction, half reaction, and we have cell potential, and then we have standard cell potential. Cell potential, we have a standard potential of half reduction, the reduction half reaction, and we need to know a lot of mathematical equations, and also there's a lot of properties of this standard potential of reduction. Okay, remember those characteristics like intensive property and how the values is related to either reducing agent or the oxidizing agent, and how we're going to use this standard potential of reduction to predict the redox reaction to take place, and how we're going to use the E0 cell to connect the free energy and the equilibrium constant, so on and so forth. Okay. So this half of a chapter is more in calculations than the concept. Okay, now we'll get to the end of chapter 19, and this is what is required, basically required for the Chem 2 class for the entire semester. And I realized that probably have some time left for chapter 25, which is nuclear chemistry, and chapter 21 for organic chemistry. And I'll look into it, and I will let you know whether we're going to cover a little bit of each two chapters. And that is it for our discussion in chapter 19. And thank you, and I see you guys later.